Hello everyone. Today, as part of a project for the course of Physics on Functional Materials, we are going to drive, abbreviated as HDD. We are going to see what is an hard drive disk, how it works, what technology it involves, and what can we expect for the future of data storage device. During this presentation, you will hear 4 different speakers. We are 4 students from the Louvain School of Engineering, currently in our first master year of Chemical Engineering and Material Science. I am Maxime and I will be the first presenter. Before another student starts to talk, you will see his head on the upper right corner of the screen. Like here, where you can see my head. So this slide gives us a little summary of what we are going to see during this video. So as I said, we will first introduce the general concept of hard disk drive and how they work. In this first section, we'll also talk a little about the evolution of hard disk drive. Then in section 2, Jimmy will introduce the basic concepts and the main properties that are involved in an HDD. So this will allow us to understand the working principle behind the reading and writing of data on an hard disk drive. In this third section, we will also talk about the concept of spintronics, which will be very useful to describe the different technology that exist to read data on an HDD. Last section, I am going to briefly present the different ideas that are studied to improve the data storage density in an hard disk drive. I will also discuss the difference between solid state disk, SSD in short, and HDD. So let's start with a little introduction. We all know, as we are future engineers, that technology is evolving very fast, and this is even more accurate when we talk about computer science and internet. We always need to store more and more data, but we don't have infinite space to store this data. Big data centers exist all around the world. They contain thousands of servers, which themselves compose of thousands of hard disk drives. The HDD technology needs to evolve with the increasing demand in data storage. So the real challenge is to increase the data storage density. This is the number of bits that can be stored per unit of surface. On this picture, we can see the evolution of an HDD that store the same amount of data, but they get smaller and smaller. This reduction in size and increase of data density was possible thanks to the evolution and the appearance of new technology like new writing head or reading heads, new reading methods, new medium or head materials. In fact, the data density is increasing because we are able to reduce the size of the bits, but in order to continue reading them, we need new and more precise technology. We will see a part of this evolution in more details in the section 3. So on the previous slide, we saw that some hard drive disk. So now I'm going to explain each element that compose an HDD and briefly discuss how it works. But before that, we are going to see a quick timeline of the hard disk drive history and the main evolution that lead to what we can find on the market today. Okay, so on this slide, what you can see on the upper left corner is the first computer using an hard drive disk that was invented in 1956 by IBM. This is the IBM LMAPR2014, and it used the IBM 350 HDD. This giant HDD weighed around a ton and was the size of two big American fridges. It was able to store 5 megabytes of data with its 50 disks and of 24 inches of diameter each. We will need to wait until 1990 to see the first big breakthrough that allowed a big increase of data density. This is the discovery of the magnetoresistance effect, MR in short terms. The picture represents the first MR reading at HDD. It's the EBM 9935, which had a capacity of 850 megabytes. Then in 1997, with the discovery of the giant magnetoresistive effect, a big democratization of the HDD happened. In fact, it was a lot easier than before to create an HDD, and it was also a lot smaller. Finally, the tunnel magnetoresistance effect gave us the hard drive disk that we know today. Industries like Seagate have managed to create an N-size HDD of 20 terabytes. So it's like 800 million times more efficient in terms of data density than the first HDD of IBM. With new improvement in this technology that we are going to see in section 4, Seagate thinks that they should reach an N-size HDD of 50 terabytes by 2024. Okay, so we can see a graph of the data density here called areal density in gigabytes per square inches through the years. So as you can see, the main technology discoveries create a new era of evolution for hard disk drive. And we are still currently in this purple zone where we use TMR head technology or tunnel magnetoresistant head technology. Okay, so now we are going to see the classic architecture of an hard drive disk. It is quite simple. There is a recording medium, which is a stack of multiple rotating glass disks that are coated with a thin layer of a certain ferromagnetic alloy. We also call them platers. It's on those platers that the data is recorded as bits with the help of a recording or writing head. The bits can then be read by one or multiple reading heads. So as a reminder, bits are series of 1 and 0 that a computer uses to store every type of data. Everything in a computer can be translated in bits. Now let's see how bits are recorded on the medium and how it can be read. There are two different methods. The first one, that was used until 2003, is the longitudinal recording. Small zones are magnetized in the same direction as the reading direction, but in two different orientations. At the boundary between two zones, there are two cases. Either the two zones are magnetized with the same orientation, either they are in opposite orientation. In the first case, there is no magnetic leakage field at the border, and the reading head treats this as a 0 bit. And in the second case, since the two zones act like very small magnets that push each other back, the magnetic leakage field is big enough for the reading head to report that as a 1 bit. So the bits are read at the borders of the little magnetized zone. It's not the same for the second recording method, which is the perpendicular one. It was discovered a lot later than the first one, and we will see why in the second section. In this case, as you can see on the slide, the bits are represented directly by the orientation of the magnetization of a small zone. For the reading and writing heads, they can access the whole surface of the disk with the help of a rotating arm. As you can see on this figure, the disk rotates on itself and the head makes small movements, small rotations that allow it to browse the whole disk. It looks simple on paper, but we have to keep in mind that the disk rotates at a speed of around 10,000 turns per minute, and so the arm must follow the rhythm. It's in fact impossible to see the head move at naked eye. The writing heads haven't changed a lot through the years, and the the technology that is used is still inductive head. However, the reading head has evolved a lot through the years. Indeed, as we said previously, the data storage density increased because we are able to reduce the size of the bits. But this reduction directly induces a weakening of the magnetic signals that are emitted by the medium. As the signals weakens, it becomes harder and harder for the reading head to detect them. And if the bit size is reduced, we then also need to increase the precision of the reading head. By the way, this is the main limitation to the increase of data density, and that's why the discovery of new reading head technology are such big breakthrough in HDD technology. And they usually trigger a brand new era for hard disk drive, as we previously saw on the graph of the evolution of HDD. Finally, to conclude this part, here's a small video that resumes what we have seen in this first section. After this video, I will let Jimmy introduce the basic concepts that play an important role in an hard drive disk.
Imagine an airplane flying 1 millimeter above the ground and circling the Earth once every 25 seconds while counting every blade of grass. Shrink all that down so that it fits in the palm of your hand, and you'd have something equivalent to a modern hard drive, an object that can likely hold more information than your local library. So how does it store so much information in such a small space? At the heart of every hard drive is a stack of high-speed spinning disks with a recording head flying over each surface. Each disk is coated with a film of microscopic, magnetized metal grains, and your data doesn't live there in a form you can recognize. Instead, it is recorded as a magnetic pattern formed by groups of those tiny grains. In each group, also known as a bit, all of the grains have their magnetizations aligned in one of two possible states, which correspond to zeros and ones. Data is written onto the disk by converting strings of bits into electrical current fed through an electromagnet. This magnet generates a field strong enough to change the direction of the metal grain's magnetization. Once this information is written onto the disk, the drive uses a magnetic reader to turn it back into a useful form, much like a phonograph needle translates a record's grooves into music.
I am Jimmy, and I will be your next speaker. I will start the discussion of the second part about the magnetic recording media until the section Magnetic Materials for Data Storage, where I will let Anatole speak. Now that the global working principle of hard disk drive has been introduced, we can look at things more in depth. Let's start by seeing exactly how the magnetic recording media works. In order to read, write, and store information, we will play with the magnetic fields produced by magnets. Many questions then come to mind. How will we utilize these fields? What type of magnetism involved and why it is used? What physical concept and phenomena must be mastered to develop HDDs? What material should be used and on what criteria? We'll try to answer on this question in what follows, but to do so, some basic principles must be reminded, such as ferromagnetism. So as you might have guessed, the type of magnetism involved is ferromagnetism. Ferromagnetism is typically described as the strongest type of magnetism. It's a physical phenomenon in which certain elements, such as iron, cobalt, nickel, and certain rare earth metals, will be able to form permanent magnets or be attracted to them. In other terms, ferromagnetic materials bear atomic magnetic moments that are easily aligned when an external field is applied. Therefore, the applied field doesn't need to be very strong, but will still result in a high magnetization of the ferromagnets. There are different origins to ferromagnetism. Rare earth metals and 3D transition metals can both be ferromagnetic, although their ferromagnetism is due to different sources. Rare earth metals have what we call localized magnetism, and unlike them, 3D transition metals do not have their own magnetic moment. Their orbital moment is equal to zero due to an interaction with the crystal field, and therefore their magnetism will be due to what we call band magnetism. It's called band magnetism because it's due to electrons of the d band. Exchange phenomena will cause an instability of said band, leading to ferromagnetism. Don't worry, this exchange phenomena will be discussed more in detail further on, but for now, let's pass on the notion of energy and magnetic domains. Magnetic domains are little regions inside the material formed by aligned magnetic moments. The material will naturally burst into magnetic domains when under the cool temperature in order to minimize the sum of the different energy terms such as the exchange energy, the Zeeman energy, the magnetocrystalline anisotropy energy, and the magnetostatic energy. The exchange energy takes into account interaction of short range and is at the origin of ferromagnetism for magnetic materials. Because of it, neighboring magnetic moments will have a tendency to align in the same direction, forming various domains. On the other hand, Zeeman energy describes the reaction the system will have to an external field. Generally, the magnetization of different domains which align to the applied field. Magnetostatic energy is the driving force for the breakup of the magnetization into domains and will be at the origin of phenomenon called shape anisotropy. Finally, there is the magnetocrystalline anisotropy energy, which translates the fact that it can take more energy to magnetize in certain direction than others. This leads us to our next point, anisotropy. An important factor to consider in order to obtain a recording medium corresponding to our application is the magnetic anisotropy. This means that the matter has magnetic properties depending on the direction, and so the magnetization will be more or less important following the direction. Since the value of bits are set with respect to the resulting direction of magnetization, this physical characteristic is crucial. There exists an energy of anisotropy which will help to describe this phenomenon. The anisotropy energy is described as EA is equal to Ku sinus squared of theta, where Ku is the anisotropy constant is joule per cubic meter, and theta is the angle between the magnetization direction and what is called the easy axis of magnetization. This energy needs to be overcome in order to magnetize the material. We can directly observe that if theta is equal to 0, there is no anisotropy energy and the magnetization direction coincides with the easy axis. The existence of an easy axis of magnetization implies that there is also a hard axis of magnetization. This can be seen on the graph depicting a uniaxial magnetic anisotropy, where the hard axis will need a much bigger external magnetic field to obtain a same magnitude of magnetization compared to the easy axis. There are different types of anisotropy, such as magnetocrystalline, magnetostatic, or shape anisotropy, magnetoelastic anisotropy, and exchange anisotropy. But we will focus on the two first, which are the most important. The magnetocrystalline type depends on the symmetry of the crystal and its own structure, such as FCC, HCP, or BCC, while the shape type will depend on the shape of the sample. The magnetocrystalline example doesn't give a clear information since there are many directions possible, but the shape example shows that there is a tendency to favor the direction in the plane for the thin film or in the needle, for example. We also see that the one in the sphere is null. I said earlier that the magnetic anisotropy is important, but why? If we take the example of a random cobalt cylinder, which is thus made of ferromagnetic material, there will be a competition for the magnetization direction. Indeed, the shape anisotropy will favor the magnetization along the AA axis on the figure, while the magnetocrystalline anisotropy will favor it along the CC axis. As a result, we have a magnetization direction in between both axes. We can then conclude that the selection of materials used for the recording and its shape are important regarding the desired recording type. The comparison between the anisotropies of ferromagnetic materials is given here. The influence of the magnetocrystalline anisotropy on the magnetization is shown on the two graphs represented here. We can observe that the anisotropy and the hard axis associated to it are much more substantial for cobalt, which has an HCP structure, compared to nickel, which has an FCC structure. On the table below, we can read that for nickel, the shape anisotropy is clearly dominant, while it is disputed for cobalt. So depending on the recorded type chosen for the medium, a specific direction of magnetization will be desired. We will choose the material depending on whether a dominant magnetostatic or magnetocrystalline anisotropy is needed. We can see the clear opposition between longitudinal and perpendicular recording. Departure recording media is a more recent technology, but we can easily understand that a dominant shape anisotropy is needed since the direction is in the plane of the different patterns. It is always a good point to remind the magnetization processes in microscopic ferromagnetic materials. On this graph, the curve of first magnetization is shown. We can observe that as the applied magnetic field increases, the magnetization will increase until reaching a maximum, but the different magnetic domains are gradually disappearing to make way for one remaining domain at magnetization maximum. In fact, as written right on the slide, the domains align along the magnetization direction, grow to the detriment of the others. Here is the general hysteresis loop for ferromagnetic materials. For the purpose of our application, we can deduce that the remnant magnetization has to be high to be able to read a bit of information precisely. Moreover, the coercive field does not have to be very high, otherwise the writing head could not magnetize the medium, but also not too low in order to prevent other unwanted sources to magnetize it. Then we can divide ferromagnetic materials into two classes. On one hand, we find soft magnetic materials which are easily magnetized and demagnetized due to their low coercivity and anisotropy. They are considered as inductor and transformer code fitting well for recording head. On the other hand, there are hard magnetic materials which are quite the opposite since they are hardly magnetized and demagnetized. They present de facto high coercivity, anisotropy, and remanence. They constitute what are called permanent magnets used for recording media. The domain wall width can be different following the materials. We will thus explain the two limit cases. The first one is abrupt, so thin, the abrupt domains walls, whose width tends to 0. Such configuration allows to minimize the anisotropy energy as all magnetic moments are aligned with the magnetization direction of the domain. On the other hand, infinite width walls allow the minimization of the exchange energy as the variation of magnetization direction between two adjacent domains become very small, on the opposite of the previous case. Finally, there is a competition between anisotropy energy and exchange energy. In real life, the domain width is determined by a compromise between those two energies that allow to minimize the sum of both of them. The wall width can be defined by the following formula where the two energies are involved. While exchange energy doesn't vary a lot from a material to another, the anisotropy energy does. It is then responsible for the major difference between the domain width of different materials. I will now let Anatole continue our presentation.
Hello, I'm Anatole and I will talk about the magnetic materials used for data storage and about the change of properties at the nanometer scale. So, the materials used in order to store magnetic data will vary based on the distinctive tasks different parts of the hard disk drive will have to accomplish. Different functions imply different properties. On one hand, we have the recording media that needs to be able to store the data as efficiently as possible. And as said a bit earlier, we want to be able to store more and more data without having to increase the disk size. That means we have to maximize the disk's areal density. This implies that the size of the magnetic grains used becomes smaller and smaller, and therefore they are more easily disturbed by heat, which is exactly what we want to avoid, since that can lead to data loss. So, for our recording media, we'll generally use a material with high magnetocrystalline anisotropy, because if the material has a strong preference for a magnetization along an easy axis, it's usually harder to unintentionally switch its magnetization. This can be explained by a concept we've talked about earlier, coercivity. Indeed, a high anisotropy and a high coercivity usually go hand in hand, yet we know the higher the coercive force, the harder it is to demagnetize the material. So we'll use what we call hard magnetic materials. Some examples of commonly used alloys are the ones containing cobalt, nickel, chromium, and platinum. On the other hand, we have the reading and writing heads. Rationally, they will have to be easily magnetized and demagnetized in order to, well, read and write the data. Therefore, we'll prefer materials that are said to be soft magnetic materials such as permara and ferrite. The constant goal about HDDs is to decrease the size of the bits to increase their performances. However, we can see some property changes when reducing the size of the bits. Under a critical radius, multi-domain ferromagnetic particles can become monodomain. If we decrease further the radius of the particles, they enter the superparamagnetic state. Here, we can see that coercivity strongly varies with the size of the particles. In the superparamagnetic state, ferromagnetic nanoparticles have no coercivity at all. It is possible to evaluate the critical radius at which a single domain particle becomes a multi-domain particle. Indeed, when the size of a single domain particle increases, its magnetostatic energy also increases. The particle will tend to become multi-domain by creating a new domain, to minimize the magnetostatic energy. However, the creation of a domain wall also costs energy. There is thus a competition between those two energies. When they are equal, the particle can become multi-domain. The magnetization of a single domain ferromagnetic particle is strongly versatile. It depends a lot of the angle between the easy axis and the direction of the external magnetic field. When it's null, the magnetization is highly remanent and the coercivity is maximal. Alternatively, when the angle is 90 degrees, there is no coercivity and the magnetization is highly reversible. To enter the superparamagnetic state, the ferromagnetic nanoparticles have to be smaller than between 5 and 30 nanometers. In this state, the magnetization direction randomly flips due to the thermal excitation. If we observe the particle, the apparent magnetization can seem to be null. Then, in the superparamagnetic state, particles have no coercivity but a high magnetic susceptibility. Superparamagnetic Superparamagnetism thus sets a minimum limit to the size of the ferromagnetic particles used to represent the bits. To switch its magnetization direction, a superparamagnetic particle has to cross an energy barrier. That barrier, whose value is obtained by the product of the anisotropy constant by the volume of the particle, can prevent the random magnetization direction flips of said particles, if it is sufficiently high. Thus, if the volume of the particle decreases, the anisotropy constant must be increased to prevent the superparamagnetic state. Now, I will talk about the reading and writing heads that are involved in HDDs. First, we will see the working principles of those technologies, and we will list the different types of reading and writing heads. So, the basic principle here is quite simple. In order to read the information stored in the disk, the reading head will convert the magnetic field of the platter into an electrical signal. Inversely, in order to write information on the disk, the writing head will convert an electrical signal into a magnetic field that will be strong enough to change the direction of the magnetization of the grains present on the platter. The electrical field will be transmitted through a U-shaped electromagnet. Initially, reading and writing heads were based on electromagnetic induction, and thus the same element was used for both of them. Since then, writing heads are still induction-based, but reading heads have seen considerable progress with the rise of spintronics. We are going to take a closer look at the main principles behind spintronics and how they tie into magnetic reading heads. Magnetoresistive technology is based on the magnetoresistive effect, which can be described as the change of a material's resistance due to a change of the magnetic field applied. When the reading head sensor detects the change of resistance, it will allow bits to be read. The first magnetoresistive heads introduced were the anisotropic magnetoresistive heads. Compared to inductive heads, they were much more sensitive to magnetic flux changes since they use spin-dependent electrical transport. Unlike electronics where the electron charge was exploited, AMR heads took interest in the electron's spin. Afterwards, AMR heads were replaced by giant magnetoresistive heads, and later on, tunneling magnetoresistive heads were proposed as an improvement to GMR heads. In what follows, we are going to consider magnetoresistive technology in greater details, but to do so, we'll need to see some reminders first. Here is a brief reminder about electric conductivity and resistance. In ferromagnetic materials, the current is carried by conduction electrons, which are close to Fermi level. The electric resistance is the result of collision of electrons with phonons, grain boundaries, or impurities deviating electrons from their initial path. Again, this is a small reminder of what we have already seen in the course of material science from last year. On the upper left corner, we can see the difference in the Fermi level of different transition metals. So, for example, for copper, the Fermi level is at the 4s orbital, and so the conduction electrons are principally from this orbital. On the other side, for iron, cobalt and nickel, the conduction electrons are from the 3d orbital. It is also important to know that conduction electrons in the 3d orbital are less mobile in terms of conductivity than those in the 4s orbital. We also already know from the course of last year that for these three metals, there is an exchange phenomenon that induces spontaneous imbalance of orbitals between spin up and spin down. Here, on the bottom left illustration, we can see that the spin up conduction electrons are called majority spin since their Fermi level is in the 4s orbital, and so they are more mobile and contribute more for the current conduction than the spin-down electrons. If you remember well the course of last year, this is this imbalance that is at the origin of ferromagnetism in transition metals. What we saw on the previous reminder will allow us to understand the spintronic concept. So, in 3D ferromagnets, current is carried in two independent channels. It is carried either by the spin-up electrons, either by the spin-down electrons. Importantly, the two spin channels have usually very different conductivities. Indeed, the electrons that carry the current can only be scattered to two states in the vicinity of the Fermi level. Hence, the scattering probability, which depends on the number of states available for scattering, is proportional to the density of state. Thus, in the figure on the slide, where the density of state at the Fermi level is much more larger for the spin-down electrons than for the spin-up electrons, electrons in the spin-down channel suffer a higher scattering rate and have a lower mobility than the electrons in the spin-up channel. It follows that there is a significant difference in resistivity for the spin-up electrons and the spin-down electrons. I will now let Kimberly talk about magnetoresistance and the different magnetoresistance heads.
Hi, my name is Kimberly, and thanks to these very useful reminders that we just saw, we're going to be able to look at the MR technologies in more detail. So, as said previously, magnetoresistance is defined as the resistance of a conductor to an external magnetic field. The magnetoresistant effect will be exploited in all three technologies, AMR, GMR, and TMR. The anisotropic magnetoresistance will depend on the value of the angle theta between the current and the magnetization field. When the electrical resistance is at its maximum, this means current and the magnetization are in parallel direction. When the electrical resistance is at its minimum, the current and magnetization are perpendicular. However, the AMR sensor sensitivity was not very high, which is why we went on to develop GMR reading heads. The transport of electrons is spin dependent. When the layers on both sides of the metallic spacer are oriented in the same direction, up in the image you see here, spin down electrons will have a very hard time passing through the layers. They will undergo collisions on both layers. While spin up electrons will be able to go through these layers easily. They represent a low resistance route. It's like if they presented a short circuit, as seen on the bottom part of the slide. So the parallel configuration is said to be the low resistance configuration. Inversely, as you've probably figured out, when the ferromagnetic layers have anti-parallel magnetizations, then they represent a high resistance configuration. Indeed, both spin-up and spin-down electrons will have a hard time passing through the layers and will undergo collisions with the layer magnetized in the opposite direction. We'll then be able to determine if we're in P or AP configuration for parallel anti-parallel configuration by measuring the voltage, since voltage is proportional to resistance. In order to read the data stored on the platter, it's quite simple, since the magnetization of the second layer of the sandwich is in the same direction as the recording medium and is thus directly related to the written data. So here's a representation of GMR resistant ratio stating that a high difference between parallel and anti-parallel resistant results in a higher reading accuracy. On the graph different GMR configurations with different size of metallic spacers are shown, and we can see that resistance is proportional to this size. A little comment about the graph, though. This is the graph that we used when we discovered the GMR reading heads. We don't use these materials because the excitation field is way too big, so we're not going to use iron and chromium, but it was a good graph to show the effects. So the simplest model of a GMR reading head architecture is illustrated here. It contains 3 layers, but generally can have much more. In this image, going from the top to the bottom, we can first see an antiferromagnetic layer, which is used to magnetically block an underlying ferromagnetic layer. Then there is a non-magnetic layer called a metallic. And finally, there is a second ferromagnetic layer, which is free to align its magnetization to the medium's magnetization. The TMR reading head architecture is quite similar to the GMR's one. The big difference is that the metallic spacer has been replaced by an insulator that will play the role of a tunnel barrier. And like for GMR heads, there will be a high resistance configuration and a low resistance configuration. This time, the high resistance configuration is the anti-parallel one, and the low resistance configuration is the parallel one. So let's take a closer look to the principle lying behind tunneling magnetoresistance. To do so, we'll have to remind some concepts you've probably seen in previous courses, such as quantum tunneling. Quantum tunneling is a property quantum particles have that allow them to pass a potential barrier even though their energy is inferior to the minimal energy required to pass. Without entering too much into details, this can be explained by the probabilistic nature of quantum mechanics. There are different parameters that will influence if the particle is more or less likely to pass through the barrier. For example, it's quite intuitive to think that the thicker the barrier and the higher the potential energy barrier to overcome, the harder it will be for the quantum particle to go through it. Another important parameter that will be particularly interesting for TMR reading heads is the density of states. The tunneling effect is proportional to the product of densities of states on both sides of the barrier, which brings us to our next point. How do we exploit this tunneling effect for reading heads? As seen previously, the architecture of TMR heads is constituted of a fixed layer where electrons are aligned in a fixed direction and a free layer where the electrons can change their direction in response to a magnetic field on the platter. These layers are separated by an insulator that will act as a barrier. That means that for electrons to be able to pass from one layer to another, naturally, they'll have to pass the barrier. The thing to keep in mind is that an electron can only tunnel to a subband of the same spin orientation. That implies we'll have once more a high resistance configuration and a low resistance configuration. On the figure, you can see that on the left side of the barrier, spin down electrons constitute the majority population and spin up electrons the minority. Inversely, on the right side of the barrier, spin down electrons represent the minority population and spin up the majority. Yet we've seen that the probability for an electron to pass a potential barrier is proportional to the product of the density of states on both sides of the barrier. This means that in both cases, we'll have a high density times a low density. Such a configuration corresponds to a high resistance state and therefore can be described as the anti-parallel configuration. So as you can see, the parallel configuration is a low resistance configuration. Here, the spin down electrons present the minority population on both sides of the barrier, and therefore the spin up electrons represents the majority population on both sides as well. This time we have the product of high densities and low densities. The product of the high densities will favor the passage of the barrier. A simple analogy would be that the minority spin acts like a short circuit, which is present in the parallel configuration. Now that we've seen AMR, GMR, and TMR, it's natural to ask which one is the best. You can see here a comparison between their performances, and off the bat, it's evident that TMR reading heads surpass both GMR and they are far more sensitive, as can be deduced by their MR ratio. On top of that, the loss of sensitivity due to temperature increase is less consequent for TMR, which is a good thing if you want to avoid the negative effects provoked by thermal agitation. Now Maxime is going to talk to you about the future of magnetic data storage and end this presentation.
Now, the last section of this presentation concerns the future of magnetic data storage and competing technologies. It will start with a brief discussion about the current and emerging technologies. Then, it will compare HDD to the other type of drives, the SSD. Here is the technology roadmap provided by the Advanced Storage Technology Consortium. It shows the evolution of the areal density with respect to years. We can read that we are currently at the maximal potential of PMR Plus technology, which consists of perpendicular recording combined to two-dimensional and shingled magnetic recording. These are techniques to optimize the compactness of tracks. We can see on the projection that there's still a lot of progress to make with the heating techniques, for example. There are also exist technique using microwaves to assist the magnetization, but it is not in the scope of this presentation. So there are many ways of improving until at least 2025, and it would represent an increase by approximately a factor of 10 in 10 years between 2015 and 2025. Now let's finish with the comparison between SSD and HDD. We have explained in detail how HDD are working during this presentation, but what about solid-state drives? Their working principles are completely different. They do not rely on magnetic rating on metallic plate, but instead they use memory chips within semiconductor materials arrange themselves into different states of electric charge to store the information. To summarize, rather than exploiting magnetic properties, they will use semiconductor properties at nanoscopic scale. Some practical comparison with key figures might be useful. As can be read on the table, the access time is way lower for SSD with 0.1 millisecond than for HDD with an access time between 2.9 and 12 milliseconds. The SSD also reads information a lot faster than the HDD, but the SSD has drawbacks as well. It has a storage capacity much more restricted compared to the HDD. Given that SSD seems to work faster than HDD, its price is also much larger for an equivalent storage capacity. These figures are approximative but still correctly portray the qualitative comparison of performance. Since both types are divergent in terms of performance, their use also differ. On one hand, SSD with their fast access to memory and reading rate are appropriate to everything which is associated to quick access, executable, and operating system in computer. On the other hand, HDD, which benefit from a large storage capacity and a democratic price in comparison, are usually used for big storage, backups, digital editing, data sharing, or server application. This concludes our presentation. Thanks for your listening.